In this lesson, we're going to go over an introduction to probability. Specifically, we'll learn the definitions of probability, outcomes, and events. We'll understand and calculate theoretical probability as well as relative frequency probability, and then we'll learn about the fundamental counting principle. So some definitions. So probability is defined as the mathematical likelihood of an event. Probability is shown by using a number between 0 and 1. So 0 means no way, not going to happen. 1 means yep, probably, definitely, for sure. Okay, so like 100% chance and a 0% chance. But you use a number between 0 and 1, or sometimes we'll express these as fractions. An event is an observation or something you can record. So for instance, if you're tossing a coin and you want heads when tossing a coin. So I like to think of event as what I want or what I'm looking for in a specific problem regarding probability. Outcomes are all of the possible results of an experiment or a trial. So going back to our coin example, you could have heads or tails, which means there's 2 outcomes. So there are 2 different types of probability that we're going to talk about. The first is theoretical. Theoretical is the number of ways an event can happen, or what you're looking for, divided by the total number of possible outcomes. Okay, so this is a division bar here. Okay. Theoretical probability is typically used for card decks, coins, dice, things like that. Experimental or relative frequency probability is the number of observations of an event over the total number of observations. So I like to think of experimental or relative frequency probability as more personal. We'll do an example later taking one of the Golden Knights players' record with how many goals they score versus how many they attempt. So when you calculate that, that is that person's experimental probability or relative frequency probability because it's based on what they're doing. Example 1. Use the theoretical model to determine the probability of the following event. A randomly selected person has a birthday in October. So with this problem, think of it in terms of days out of the year, not necessarily months. So in this case, our event is having a birthday in October. Our outcomes would be all possible days of the year. Okay, so for the denominator, we know that there's 365 days in a year. And how many days are there in October? There are 31. And I don't know if you learned this trick. A lot of my students haven't, but you can use your knuckles to determine how many days there are in a month. Let me see if I can get this to work on camera. So you would start here. So this would be January, February, March, April, May, June, July, August, September, October, November, December. So any month that falls on the knuckle has 31 days, and any month that falls in between the space, except February, has 30 days. So you can use that when determining these problems. Example 2, a 6-sided die is tossed once. Find the probability of rolling a 2. So in terms of our event, we want to roll a 2. That's what we want, and there's one way to do that. Okay, there's only 1 2 on a 6-sided die. Our outcomes are the numbers 1 through 6. So there are 6 possible outcomes, so the probability of rolling a 2 is 1 out of 6. Determine the probability of tossing a fair coin twice and getting 2 tails. So for this problem, it's a little bit easier to visualize what's happening here before we jump into event and outcomes. So when we toss a fair coin, let's list all of our possible ways. We could get heads first, and then heads again. So this is toss 1 and toss 2. We could get heads and then tails. We could get tails, then heads, or tails, then tails. So what this chart does for us is it tells us that there's 4 possible outcomes. And what we want is we want 2 tails, which means that we're looking for one of those. So in this case, the probability would be 1 over 4 or 0.25 or 25% chance of that happening. Probability with cards. So take a picture of this in your notes or copy it into your notes. This is how a deck of cards is built. There are 52 playing cards total. The suits are clubs, diamonds, hearts, and spades. There's 13 of each. Okay. Let me see. That means there would be 26 red cards, and if we look at the outer, there's also 26 black cards. Our cards here, the cards that have faces on them, are called face cards. We have Jack, Queen, and King. And the A over here is our ace. My dad was a dealer at one of the casinos, so I grew up knowing how to play cards. But make sure, I know that's not true for everyone, so make sure that you know this chart, okay? So an experiment consists of drawing one card from a standard 52 card deck. What is the probability of drawing a red card? So with these card problems, if you're drawing one card from a standard 52 card deck, your outcomes, there's always 52 possible outcomes, okay? Because that's the total number of possible results, as you could have any of those 52. A red card, if you go to your chart, red card could be anything. It could be a diamond or a heart. It doesn't matter. All this person wants is a red card. There's 26 of those. So your probability would be 26 out of 52 or 0.5, which makes sense because half the deck are red cards. Part B, probability of drawing a 7. So it doesn't matter which 7. It doesn't specify a suit. So if we look, there are 4 7s in the deck. So in terms of our event, we'd be happy with any one of those 4. And out of the possible outcomes, there's 52. So you take 4 divided by 52. Doesn't tell us where to round. Say 0.77. Okay, let's say this problem said 7 of hearts. In that case, there's only one 7 of hearts. So that would be 1 out of 52. So I just wanted to show that to you because sometimes these probability problems do specify a specific suit for the card. Part C, king or an ace. So when you see the word or in there, you'd be happy with a king or you'd be happy with an ace. So both of those count in your events. There's 4 kings and there's 4 aces. So when you're determining your events, you'd be happy with either one. So you add those two together, and then out of the total is 52. So this probability here would be 8 out of 52, because you'd be happy with any one of those, king or ace. 8 cards is, any of those 8 is what you want out of the total deck, which is 52. Part D, a red or a black card. So there are, again, 26 red cards, 26 black cards. You'd be happy with either of them out of 52. 52 out of 52, which is 1. Makes sense. You have a 100% chance of drawing a red or a black card from the standard 52 card deck. Example 5. Mark Stone has made 21 goals in 168 attempts. Based on his performance, what is the relative frequency probability that he will make his next goal? So, like I mentioned, the way that I think about relative frequency probability is something that's personal or based on a specific person for the examples that we do. So Mark Stone has made 21 goals in his 168 attempts. So we're not looking for the probability that just anyone will score a goal. We're looking for the probability that Mark Stone will score a goal on his next attempt. So we take what we want, or what we want to happen, which is our scoring a goal, which has happened 21 times in the past, out of our total number of observations. So let me not use the word outcome. And we've seen that out of 168 times. So Mark Stone's relative frequency probability would be 21 divided by 168, which is 0.125. Application. So in dealing with probability, we would discuss this if we were in class. Since a lottery ticket is either a winning ticket or a losing ticket, the probability of my ticket being a winning ticket is 0.5 or 50%. That is false. So this is an oversimplification of probability. When you say something like this, or when this person says something that the probability of a winning ticket is 0.5, they're assuming that a winning ticket and a losing ticket are equally likely, which we know from the lottery that that's not true. You're a lot more likely to get a losing ticket than a winning ticket. So this would be an oversimplification of probability. Next, we'll talk about the fundamental counting principle. So depending on the type of probability problem you're working on, this principle may come in handy. So it's a way to determine the number of outcomes. So for instance, if I have 2 shirts and 3 pairs of pants, how many outfits can you make? So let's say we have shirt 1 and shirt 2. Let's say we have pants 1, pants 2, and pants 3. So let's map this out. You could pair shirt 1 with pants 1, shirt 1 with pants 2, or shirt 1 with pants 3. And those are all the possibilities of pairing shirt 1. Let's talk about shirt 2. You could pair it with pants 1, you could pair it with pants 2, or you could pair it with pants 3. So this would give us 6 outfits. The wardrobe may be more robust than you thought. Okay, or another way to do this is to take what we're given and just multiply 2 times 3, which would also give us 6. So going back to the tossing a coin twice, this could have helped us there because there were 2 possibilities on the first toss, 2 possibilities on the second toss. If we would have multiplied those together, we would have gotten 4. Thank you for watching. If you have any questions, please feel free to reach out to me.